Hello, good day, and welcome to today's presentation on Legendre Polynomial-based Attention mechanism in dual branch hybrid 5 towards arithmetic diagnosis. This is the outline of the presentation. We'll look at the introduction section. We have the methodology section, the experimental results, and our findings. Let's begin with the background. Arrhythmia is a major concern. It's a major health concern, and according to WHO, it accounted for 17 million deaths. And also, early detection of arrhythmia could be beneficial to the human health and the world at large. But manual interpretation are somehow or often prone to errors and resource constraints. Again, physicians or cardiologists' manual assessments of ECG signal is very time consuming, and this calls for an automated and accurate diagnosis of arrhythmia. So without wasting much time, let's move on to the motivation aspects of the study. What motivated us? The study is motivated to use deep learning in the diagnosis of cardiac anomalies or abnormalities in electrocardiogram signals. This often reduces the dependence of human expertise and also improves generalizability of the classification of these arrhythmia conditions. Employing deep learning models alleviates the pressure on medical practitioners. So these are the main motivations why we conducted this study. Let's look at the contributions. We proposed a Legendre polynomial attention base to capture temporal dependencies, and also we propose a dual branch ResNet 5 model to improve arrhythmia diagnosis. And it was noted that our approach performed well than the state-of-the-art models. So let's look at the methodology aspect. We look at the data set. The study employed the MIT Arrhythmia database, which contains 48-hour recordings from 48 patients. These signals were sampled at 360 Hz, and the data set contains 100,012 signals, and this is the summary of the data sets, with normal sinus rhythm having 75,011. Okay, these signals were decomposed using the discrete wavelet transform to decompose the signals into units using a low pass filter and then the high pass filter. The low pass filter is responsible for approximation coefficients, while the high pass filter is responsible for the detail coefficients. After signal decomposition, noise were removed using a soft threshold approach. So if the decomposed signal has or is greater than a certain threshold, then we subtract the threshold from the signal to remove the noise. So if the decomposed signal is also less than or equal to the soft threshold, nothing is done to the signal because it is already clean. Also, if the threshold is less than the decomposed signal, we add the threshold to the decomposed signal to remove the noise. Also, we performed data normalization to transform the data into an acceptable level that can be used to train the models. let's look at the sample models. The sample signals. This is the original signal. You see, it's very noisy, and after denoising, this is the signal, how it looks, and then after the normalization procedure, this is what we have here. We can look at the calibrations on the y-axis or the y-coordinates as compared to this one to verify the normalization procedure. All right, so let's move on to the proposed attention mechanism, the Legendre polynomial-based attention mechanism. Supposing we have a signal xn, we generate Legendre polynomials, and then leveraging the power of the orthogonal property of the Legendre polynomials, these features were generated, and these features were multiplied by the inputs matrix, which is t by f, time t representing time steps and f is the features. So there is an interaction that goes on between the transpose of the inputs data and the Legendre polynomial features. So after the interaction from the inputs and then the Legendre polynomial features, a weight matrix of size t by t is multiplied by the interaction matrix to get an output. So this is the architecture of the proposed LegPoBA mechanism. Let's move on to the DBRH-5 model. The model consists of three key components. We have the dual branch, which serves as the feature extractor. It contains convolutional layers and max pooling layers, together with the proposed LegPoBA, that's the Legendre polynomial attention-based mechanism that aids in feature enhancement. All right, so the first branch has two convolutional layers, two attention layers, and two max pool layers. The same thing also applies to the second channel. Here, the study employed 4 hertz and 32 dimensions for the attention mechanism. So the features from these two branches are added, and then it is subjected to a pre-trained model. Here we use the ResNet 50 model, followed by the attention model, the proposed attention model, and then a global average pooling to extract global features. And these features from the global average pooling layer goes through the classified layer. The classified layer is made up of fully commutated layers, 1024, and a drop out of 30%, and the predicted output. So this is the residual block of the ResNet 50. All right, let's move on to the results of this study. For the classification results, the study or the authors compared or reported on the class-wise classification, and this is the results that shows that the proposed model did a great job. We have the average accuracy of 99.53, PPV, the average that's a precision. We have 99.77, sensitivity 99.71, specificity 99.94%, and then F1 score of 99.77%. Also, the proposed model was compared against some state-of-the-art models, and here it is only the ResNet 101 model that came closer to the proposed model, which is 99%, as compared to our model 99.5%. And the proposed model also excelled in all the metrics compared to its competitors. All right, let's look at the confusion matrices of these models. it can be seen that the ResNet model, ResNet 101, ResNet 152, and then DenseNet 169 struggled in classifying the normal sinus rhythm, as well as the inception V3 and ResNet 101. But for our proposed DBRH-5 model, the model got a nearly perfection classification, with the leading diagonal being 1 throughout. All right, let's move on to some visualization of the classified test samples on the test data. It can be seen that DBRH-5, our proposed model, did a great job here, followed by a ResNet 101, and Inception V3 struggled in the classification performance, as well as ResNet 101. Let's move on to comparison with, we are still with the comparison of the state-of-the-art models with respect to the errors. With respect to parameter counts, then gigabyte flops, and then inference times. The proposed DBRH-5 model, despite its less parameter counts as compared to its competitors, its computation was very low, which is 0.45 gigabytes, and it was only Inception V3 that came closer in terms of less computation, but it is not as lower as the DBRH-5 model. With respect to inference time, the model did a great job by classifying samples of ECG recordings using just 0.18 seconds. The proposed model was evaluated to evaluate the errors after prediction. So for the mean squared error, the error measured 0.21 percent, which is less than 1%, same as mean average error 0.78, less than 1%, but it was only the root mean square error that recorded a 4.53%. Let's kindly move on to the next slide. So to determine the effectiveness of the attention mechanism, the proposed attention mechanism, the study sought to the use of a hypothesis test. So at an alpha level of 0.05, the null hypothesis stated that there is no difference between the classification results between the model with and without the attention mechanism. And also, the alternate hypothesis, which is the claim, says that there is a significant difference between the two models. So let's look at the results. The results stated that the probability value or the p-value were all less than the alpha level of 0.05. So our decision is to reject the null hypothesis. So this means that there was a great improvement with the introduction of the attention mechanism in the classification task. All right, our findings. This study proposed a novel approach using the power of the orthogonal properties of the Legendre polynomials to classify arrhythmia, or to classify signals in the diagnosis of arrhythmia. Also, the attention mechanism, when integrated into the proposed DBR5 model, improves the classification performance. That is, the LegPoBA, or the attention mechanism, increased the model's performance by 4.35% in accuracy, and the test statistics for the mean squared error, the root mean squared error, and the mean average error indicate that the errors were less than 1%. Thank you. Questions?